Okay, in this class, we are going to discuss series LCR circuit. Personally, I find this topic slightly confusing, so we are going to be slow. We are going to be slow. We have series LCR circuit, so obviously we have an inductor, and we have a capacitor, and we have a resistor, and obviously we have a source of EMF. Okay, inductor is L, capacitor is C, resistor is R, and this is the EMF. We don't know it. Okay, so what we know? We know the current. Current is I is equal to I naught sine omega t. So we know its peak value, we know the phase. We know the phase angle with respect to time. And what we have to find? We have to find the peak value of the EMF. We also have to find the phase angle of the EMF. So what we are going to do? We are going to apply Kirchhoff voltage law. Applying Kirchhoff voltage law. This is the source voltage. So we are applying this voltage. We are giving this voltage. Some voltage is consumed here, and that will be minus LdI by dt, and some voltage is consumed here, which will be minus Q by C. Okay, voltage consumed is Q by C, but voltage is Q by C. Okay, voltage drop, and here voltage drop will be minus IR, and total will be 0. So what we have to find? We have to find this EMF, which is LdI by dt plus Q by C plus IR. So what is happening? I will explain again. We are providing some voltage, and some voltage is consumed by the resistor, some voltage is consumed by the inductor, some voltage is consumed by the capacitor. Okay, and we are going to find the sum of all these consumed voltages. Okay, sum of all these consumed voltages, it will give us the applied EMF. So this part is easy. L di by dt. Di by dt means current. We have to integrate differentiate this thing. So what will be di by dt? Di by dt will be I naught omega cos omega t, right? So L was already there, and we will write I naught omega cos omega t. Okay, now Q by C. Q means what is Q? Q will be integration. Q is actually integration of the current. Okay, integration of the current. Integration of the current. So let us integrate this. Q will be I dt integration. And what is the integration of this current? Integration of this current will be I naught by omega minus cos omega t. Minus cos omega t. So 1 by C is already there. 1 by C is already there. So it will become minus I naught by omega C cos omega t. Okay, now you can see that I have, when we did the integration, I did not write the constant part. Okay, this part is explained in previous topics also, previous videos also. what is happening? Net charge flow in a circuit is going to be zero over a period of time. One period, two period, n number of period. On an average, there is no charge flow. Sometimes this charge is going to be positive, sometimes it is going to be negative. On an average, it is going to be zero. Until and unless there is a DC source, net charge flow is going to be zero over n number of period of time. So there is no possibility of constant part. Okay, we have actually explained this thing. And the last part, IR, that is easy. IR is simply I naught R sine omega t. Okay, I naught sine omega t. So this part, this has a name. This is voltage drop across the resistor. Okay, and this has a name. We call it voltage drop across the inductor, and this is the voltage drop across the capacitor. What we can see, voltage drop across the inductor and capacitor, they are simply opposite, right? The sign is negative, right? One sign is positive, other sign is negative. Both are cos, but positive negative. That means if the voltage across the inductor is positive, voltage across the capacitor will be negative. Okay, and vice versa. Also, these voltages can be, in a particular case, can be equal and opposite. So they will both cancel out. That is the case of resonance. Okay, suppose this underlined part and this underlined part is equal. So what will happen? Both will be equal and opposite. They will simply cancel out, and we will get only I naught R sine omega t. So all these things I am going to do in the next page. So I will show the reference axis. This is our reference axis, and I will show you the current phasor. Okay, current phasor was this way. I will call it I. Okay, and current phasor was omega t angle. Current phasor was making omega t angle with the reference axis. Okay, because equation of the current was I naught sine omega t, right? Sine omega t. And what about the voltage drop across the resistor? This was in phase, right? We got sine. Okay, so this VR was I naught R sine omega t. Same phase, right? But voltage drop across the inductor was something different. Okay, it was I naught omega L cos omega t. Okay, so we already know this part. Okay, sine omega t and cos omega t, they are pi by 2 angle apart. Okay, if one phasor is sine omega t, other phasor is cos omega t, cos omega t will be leading by an angle pi by 2. I will show you again. So cos omega t is what? Sine omega t plus pi by 2. So we know this thing. Okay, voltage across the inductor leads by an angle 90 degree. What about the voltage across the capacitor? It lags. It lags by an angle again 90 degree. Okay. So minus 1 by omega c, I naught by omega c cos omega t plus pi by 2. Some people will say I have again written plus pi by 2, not minus pi by 2. If you remove this minus sign, you will get this thing. Uh, yeah. So you can see that I will write here also in terms of sign. So this is sine omega t plus pi by 2. This is sine omega t minus pi by 2. Okay. And if you write in terms of cos, we are getting a minus. There is no minus here. So they are just opposite. Okay. Now I will try to simplify this thing. We have a reference axis. Okay. And we have VR this way, and we have VL minus VC this way. Okay, so this VR, this is VR. Okay, I will write VR I naught R sine omega t. Okay, the magnitude, the length is I naught R. This length is I naught R. Okay, remember this. This is for the phase consideration, and this length is omega L minus 1 by omega c. Okay, sine omega t plus pi by 2. You can also say cos pi by 2. So the length of this part is what? Omega L minus 1 by omega c. Now we have two phasors at 90-degree angle. We can find its length easily. We can find its length using the parallelogram law, using the triangle law. Okay, you know that we are going to add phasors just like vectors. Okay, mathematically phasors and vectors, their mathematics is same, and this angle is alpha. So this phasor will be, this phasor which was E actually, this phasor will be, length will be I naught R square, I naught R square. Here also we have I naught. Okay, here I did not write I naught. This square. Okay, omega L minus 1 by omega c plus omega L minus 1 by omega c, the whole square. And for phase consideration I will write sine omega t. Omega t is this angle. Okay, this angle is omega t, but we have to write omega t plus alpha. Omega t plus alpha, and what will be alpha? Tan alpha will be, tan alpha will be this length, tan alpha will be this length, which is omega L minus 1 by omega c, which is omega L minus 1 by omega c, divided by this length, which is r, I naught r. Okay, it is I naught r, and this is I naught omega L minus 1 by omega c. Okay, so this is our, okay, this is our alpha. Okay, you can see that if omega L minus 1 by omega c, I will not write this way. If omega L greater than 1 by omega c, if omega L greater than omega c, alpha is a positive angle. Okay, alpha is a positive angle. That means this is a positive angle and EMF will be leading. Okay, so I will write this thing on the next page. Our current was I is equal to I naught sine omega t, and our EMF was I naught r square plus omega L minus 1 by omega c, the whole square sine omega t plus alpha, and here we have alpha tan inverse omega L minus 1 by omega c divided by r. Okay, if omega L greater than omega c 1 by omega c, then tan alpha, sorry, alpha is positive, alpha is positive, EMF, E will lead I. Okay, EMF will lead the current. If omega L is less than omega c, then alpha is less than 0, E will lag the current, EMF will lag the current. If omega L is equal to omega c, omega or omega is 1 by root LC, we will see no lag or lead. There will be no lag or lead. Okay, that means in this particular frequency omega naught, in this particular frequency, angular frequency omega naught, WL and WC 1 by WC, they will cancel out. Voltage across the capacitor and voltage across the inductor will be simply opposite of each other. They will simply cancel out. If one of them is consuming power, other will be expending power. Okay, and all the voltage will appear across the resistor. And what we need to see, this part. Okay, this part is called impedance. Impedance r square plus wl minus 1 by wc, the whole square under root. Impedance, this is impedance, and you can see that if impedance is high, I naught will be E naught by r square plus r square plus omega L minus 1 by omega c, and it is also so basically same relationship is true for RMS current and RMS voltage also. IRMS, ERMS, peak value of I, peak value of EMF. Okay, so this part is called, this thing is called impedance. Let us see, we have R square, but let us consider this part. Impedance will be maximum when this part becomes 0. Impedance will be maximum when this part becomes 0. That means we have a particular frequency at which impedance is minimum, and that case is called resonance. In this case, current will be highest for a given voltage. Okay, for a given voltage, current will be highest. What if angular frequency is larger than this? If angular frequency is larger than this, omega L will be larger than omega C. Let us say omega is very large. If omega is very large, we called it inductive reactance. Inductive reactance will be very high compared to capacitive reactance. Basically, because of the inductor, it will feel the impedance will be very high. Okay, so that means inductor will not allow the passage of high frequency current. Okay, inductor will not allow the passage of high frequency current. And let us see what will happen if omega is very small. Suppose omega is close to 0, this omega c 1 by omega c will be very high. Okay, overall this thing will become very high and impedance will again become very high. So impedance will become very high because of this 1 by omega c if omega value is very low. That means if the frequency is very small, the capacitor will hinder the flow of charge, flow of current. Okay, capacitor will hinder the flow of current. Okay, this happens. For example, for DC current, omega is 0. Okay, there is no back and forth motion of charges. Okay, there is no alternating current. Okay, so for DC current, omega is what? 0. And we know that capacitor will block the flow of current. Okay, flow of current in DC. Finally, it will get charged and then it will block. While inductor will not block. Okay, now we understand all this part. We understand this tan alpha part also, and I will define one more thing which is called power factor. Power factor is cos alpha. Tan alpha is this, right? Tan alpha is omega L minus 1 by omega c divided by r. So cos alpha will be r by r square plus omega L minus 1 by omega c the whole square under root. Okay, this will be our power factor. Looks like okay. So why are we defining this power factor? We will see in the next slide. But one more thing, I actually I wanted to take the EMF source and I wanted to find the current, but looks like it will be lengthy. But I will do it in short. Okay, suppose we have a EMF E naught sine omega t, then and we have an inductor and we have a capacitor and we have a resistor. Okay, and in this case you will see that current will be E naught by r square plus omega L minus 1 by omega c sine omega t minus alpha. Okay, so in the previous example what we did, we wrote the current was I naught sine omega t, and we got what we got a equation for voltage, and here I have taken the voltage and I have found the current. Okay, again 10 alpha, but I have written a minus here. Here current is lagging. In previous chapter voltage was leading. Okay, so that is the same thing. Okay, and I am doing mistake here. Now we will discuss about power dissipation in AC circuit. Power dissipation in AC circuit. Power dissipation in LCR circuit. LCR circuit means AC circuit. Okay, we are not talking about DC circuit. So one thing I would like to remind you, average value of sine square omega t was half. Average value of cos square omega t, I am talking about one time period, it was also half. Average value of sine omega t over one time period is 0. Average value of cos omega t over one time period is 0. Average value of sine 2 omega t over one time period is also 0. Okay, these are the result we have already discussed. Okay, these are the result we have already discussed. Now power, instantaneous power, for instantaneous power what I will write, I naught sine omega t into I naught z sine omega t plus alpha, right? This is what I am going to write. So this is instantaneous power, but average power will be I naught square z, and average value of sine omega t into sine omega t plus alpha. Okay, now this part is constant, right? And we have to find the average value of this part. Okay, now I will write it directly. No, I will not write it directly. Okay, I will do it. So we have to find average value of sine omega t into sine omega t into cos alpha plus cos omega t into sine alpha. Okay, this was sine omega t, this was sine omega t, and this is what uh, I am expanding sine omega t into cos alpha, cos omega t into sine alpha. Okay, we are trying to find the average value of this thing first. So this will become sine square omega t into cos alpha plus average value of sine omega t cos omega t into sine alpha. Okay, so this will be half. Average value of sine square omega t is half, and this is half cos alpha plus this will become sine 2 omega t divided by 2, and sine 2 omega t or cos 2 omega t over one time period, this will be 0. Okay, one time period means in time t is equal to 2 pi by omega, this thing is going to be 0, so this will be 0. So what I am going to get for this part, I am going to get half. So P average I am writing here also. P here is I naught squared Z by 2 into cos alpha, and I will write it here also. P average will be I know IRMS. Okay, okay, let me write it. I naught by root 2 the whole squared Z cos alpha. Okay, so this is what IRMS the whole square into Z cos alpha. The same thing can also be written as IRMS into IRMS into Z into cos alpha. So it is like IRMS VRMS into cos alpha. Okay, so this is P average. In purely resistive circuit, what we got, it was just IRMS VRMS. Okay, but here we are getting one more thing, that is cos alpha. That is what? Cos alpha. This thing is called power factor. Okay, because of the phase difference, the power dissipation will be less than IRMS into VRMS. Okay, we have also discussed purely capacitive circuit. What we discussed in purely capacitive circuit, the phase angle was 90 degree. Phase angle between the current and voltage was 90 degree, and because it was 90 degree, power dissipation, average power was 0. We also discussed the same thing in purely inductive circuit. There also, in purely inductive circuit, voltage was leading the current by an angle pi by 2, and power dissipation there also was 0. So it looks like it reminds me something from mechanics. So what will happen? What is happening here? Suppose this is a current phasor, and suppose it is a voltage phasor. Okay, an angle between them is alpha, and phase angle between them is alpha. So this is IRMS. Okay, and this is what? VRMS. Then this IRMS has two parts. Okay, this IRMS has two parts. I will show it by dotted and dotted vectors, dotted phasors actually. Okay, hmm. So this part, this part is IRMS cos alpha, and this part is IRMS sin alpha. Okay, so this IRMS cos alpha, because of this IRMS cos alpha, power is getting dissipated, and because of this IRMS sin alpha, power is not getting dissipated. Okay, and so this is called wattless current. Okay, wattless current. Okay, in purely inductive circuit, this part will be maximum. Everything is wattless current. Okay, no power dissipation happens, and in purely resistive circuit, everything is the wattage current. Okay, which is producing heat dissipation. Now, what we are going to do, let us write things. Okay, so P can be also written this way: VRMS I will be VRMS by Z, and cos alpha will be R by Z. This is cos alpha. Okay, cos alpha will be R by Z. So power dissipation can also be written like this: VRMS the whole square by Z square. This is basically I square. Okay, IRMS the whole square, and this is what? R. Okay, now what we are going to discuss, we are going to discuss the resonance part. In what happens in resonance part, we have a, okay, I will write it again: VRMS the whole square by R square plus omega L minus 1 by omega C the whole square into R. In resonance, what happens? This part becomes 0, okay, and we will get the maximum power output. Okay, maximum average power. Okay, resonance, when omega L is 1 by omega C, we have this particular frequency at which both are equal, and this particular frequency is 1 by root LC. uh, Z will become, impedance is simply R, and alpha is 0, no phase difference. Okay, and power will be VRMS the whole square by R, or IRMS the whole square into R. Okay, in this case power dissipation will be maximum. I will write the thing again, and okay, yes, this is, so you can see that in this particular case this part will become 0, and it will simply become VRMS the whole square by R. Okay, or IRMS the whole square into R. That means it will give you maximum power. Okay, this is the case of resonance, and how it is used in our daily life we will discuss about it. Okay, we will discuss about it. We have seen some radio, right? What happens in radio, in FM, at a particular frequency, uh, it catches the signal, very clearly, right? At a particular frequency, radio FM catches the signal very clearly. That means for that particular frequency, for that particular frequency, power dissipation is maximum. Okay, this part is almost 0. Power dissipation is what? Maximum. Okay, so we have one frequency, right? We have upper, okay, angular frequency, and we have this frequency, this is called resonant frequency, right? Resonant frequency. We have